Section 4.4 is going to talk about concavity, which is kind of a subtle nuance about the shape of a graph. And I can kind of explain concavity if we look at this picture. So from left to right, as you look at this function, the function is increasing, right? But does something interesting happen at 2? I mean, relative to the graph? Is something strange happening? What changes from to the left of 2 to the right of 2? Yeah, the concavity, the shape of the graph. Now, to the left of this point, the function has what's called a concave down shape. To the right, it has a concave up shape. Now, without going through all the details, you can analyze the derivative of the graph, and the derivative is going to tell you where a function is increasing and decreasing, and then its second derivative is going to tell you where the function is concave up or the function is concave down. So let me kind of skip ahead a little bit. Talk about concavity. We're going to be testing concavity with the second derivative. So I think that's defined in your book. Let me give you the short version of it. So the second derivative test. Basically, it's this. If f double prime of x is greater than 0, then your function is concave up. So if then f of x has a concave up shape. If f double prime of x is less than 0, then f of x has what? Yeah, concave down shape. All right, so one of those two things is going to happen. Otherwise, you know, if one of those doesn't happen, then you got a constant function. But one of those things is going to happen. In working with our functions, we're going to have to look at their second derivatives and do the same kind of testing that we did in section 4.3. Let's start with problem number 4. H of x is x to the 5th minus 5x plus 2. Now the nice thing about this is a warm-up example is that it's a polynomial. It's defined everywhere. We don't have to worry about, you know, something changing signs at vertical asymptotes, etc. The first derivative would be 5x to the 4th minus 5. The second derivative would be 20x cubed. And I want to know where this can change signs. Well, it can only change signs where this actually equals 0. So where is that going to happen? At x equals 0. Thank you. So at x equals 0, it can change signs. So great. Let's just keep track of a few things here. So you got x, f double prime, and then we'll put our point here at 0. Now at 0, the second derivative is 0. The actual value of the function, I shouldn't be putting an f, I should probably put an h here. H double prime. But at h of 0, the function is at 2. Okay, I mean, when we start graphing these things, that'll be more important to keep track of that. But for now, I want to do some testing. I want to test not the first derivative, but the second derivative. So I need some test points. What will be a test point to the left of 0? Negative 1 and 1. Do I need to put that in my graphing calculator to test that one? Now, Shane, what happens if I plug in a negative 1? What's the sign of the second derivative going to be? Negative. And at positive 1, the derivative is going to be, or second derivative is going to be positive. So negative and positive. Now I'm interested in knowing that they're negative and positive because that tells me about the shape of the function. It's going to be concave down and then concave up. We should see that when you look at the graph. And there's nothing wrong with taking time to verify that. And I'll just take a quick second and verify it using Desmos. So let's get rid of this real quick. Let's take a look at, now what should it be plotting, the function or the second derivative? The function, because I want to see its correspondence to its what we calculated from the second derivative. 5x plus 2. And let's kind of zoom out a little bit. So the function has a concave down shape until you get to 0. Now the function is decreasing as you move across 0. It's still decreasing from here down to here. But the shape changes. It changes right here from concave down to concave up. And loosely speaking, concave down is a shape that spills water. Concave up is a shape that's going to hold water. So that's a nice loosely formed definition of that. It's a good working definition. There are a couple instances where it doesn't really work, but more or less that's going to get all your work done for you. It matches our conclusions here. So going back here to the graph or to our work, it's concave up on 0 to infinity, and concave down on negative infinity to 0. That's what we're looking for in this section, is that kind of a shape, or knowing things about that shape. Let's continue with problem number 8, unless there's some thoughts on problem number 4 still. So, moving up to problem number 8. This is another one of those where it's helpful if you're a little bit thoughtful in working with the derivative. For problem number 8, y equals negative 3x to the 5th plus 40x cubed plus 135x divided by 270. Ooh. Derivative of this looks like it's going to be a little bit of a pain. I hope you don't use the quotient rule. I really hope you don't use the quotient rule. All right, there'd be 2 of us that'd be unhappy if you did that. You should rewrite that by writing the 1 over 270 as like a constant out in front. And now let's work on finding some derivatives. Again, this is a polynomial, so it's defined for all manner of different values of x's. Its domain is negative infinity to infinity, so we're good in that shape. Y prime is going to be 1 over 270 times what? It's going to be negative 15 x to the 4th plus 120 x squared plus 135. Okay. We need to calculate the second derivative. I'm not sure if you see it here or not, but all these numbers are divisible by 15, and that can cancel here. Tell you what, let's just hold off on that, cleaning that up until we get to the second derivative. Y double prime is 1 over 270 times negative 60 x to the 3rd plus 240 x, and very nicely the 135 drops off. Okay, that's helpful. I would suggest that we factor out, say, a negative 60x. So negative 60x over 270. If I factor out a negative 60x, what am I leaving behind? X squared. Well, 240 divided by 60 would be 4. Now this is going to simplify even more, right? Because 60 and 270 share some common factors. You can cancel out the trailing 0 real quick. That's like dividing by 10. And then 6 and 27 share a factor of 3. So this is negative 2/9 x times x minus 2 times x plus 2. Getting it factored is really an important step here. Why is that? Because once it's factored, we can easily set and solve this equation equal to 0. Baldine, what are our solutions here for x? Good. And you can read that off. 2, negative 2, and 0. Well, we're going to have to do that testing thing again. So x, y, y double prime, negative 2, 0, and 2. So at these points, the second derivative is always 0. That's fine. We need to decide what's happening to this function between here. Is it positive? Is it negative, etc.? What do you suggest? How do I determine the sign in between those 2 points? Or sign of these things? Yeah, plug it into your calculator, right? So let's think here. Some good test points would be, say, negative 3, negative 1, 1, and 3. And let's see. I think it's going to test out as negative, positive, negative, positive. Pretty sure. Did anyone race ahead on me on that one? Okay, thank you. So if that's the case, then the function is concave up, concave down, concave up, concave down. Now concave up and concave down do not have to match where the function is increasing and decreasing. Oftentimes they don't. So let's see, concave up would be on the interval from what to what? Negative infinity, negative 2, and 0 to 2. And then concave down will be on the interval negative 2 to 0, and the last one, 2 to infinity. Now eventually we're going to be putting these things together with some graphing. One of the things that I'm going to give you a heads up on is that you're going to need to be good with your factoring. We'll work on problem number 20 next time. You might want to start look at it ahead of time. It won't hurt. But factoring there is going to be a challenge, and it's something you have to pay attention to. For now, for homework, just try problems 1 through 17. I will do problem number 18 next week. Remind me. It's a good one, and you need practice on that. Have a good week.